so strong, yeah.
Hello everyone, welcome to CocoaHeads 165. Thanks for coming, it's great to see everyone. In the spirit of reconciliation, Melbourne CocoaHeads acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islanders people today. Our speakers for tonight, Amy Dells, who's starting off with the month that was, which, you know, it's good to see that back again. Simon Whitty, whose presentation is called FlyingFox, nice. Neo with Structured Concurrency, and then Rob Amos is going to tell us about Unbreakable API Contracts at ANZ with gRPC. We've got a code of conduct here at CocoaHeads. If you're being harassed or notice anyone else being harassed or notice uncomfortable situations, please tell one of the organisers, or there's an online form as well to fill out at the melbournecocoaheads.com/code of conduct. Some housekeeping. The toilets are outside past the elevators to the right, and then the emergency exits are just near the toilets as well. Hopefully people are wearing name tags. But yeah, organisers of CocoaHeads will have a little new badge now. Is that hopefully? Yeah, is that in play? Yep. And then new people will be wearing a little blue dot. So if you see someone with a blue dot, make them feel welcome and, you know, welcome new people to the community. Just for questions, we have like an online viewers as well, so don't just yell out to ask questions, put your hand up and we'll bring a mic out to you so everyone can hear. And if you're online, put your questions in Slack and we'll read it out to everyone. There's stickers at the door. You're welcome to take as many as you like. Put them on laptops and bags. Thank you to our sponsors, Itty Bitty Apps. Here they're wonderful. They're our gold sponsor. We couldn't do it without them. And Baloo, our silver sponsor. They're great too. Thank you for helping us make these nights possible. We've got some other events coming up. Hack Night on next Wednesday, the 17th of May. I think what time does that start? 6? No, 5. Yeah, okay. Yeah, so that's pretty good. Bring your laptop and just code and ask people for help or share what you're working on with others. There's the drink night coming up on the last Tuesday of the month, so that's the 30th of May. Was there a big turnout last time? Sadly not. Oh, that's right. Yeah. Conflict. And then next month as well, we've got Beyond WWDC, so 14th of June. So do you want to give any pitch on that or?
Suppose I can. Yeah. So if you were here last year, Beyond WWDC was an event we ran with Apple. We had a panel session, which was awesome, and then some Apple folk here answering questions. We are partnering with Apple again this year for this year's event. They haven't told us what they're doing yet though, so apparently it's good, but we'll have to wait and see.
So information to come.
Yeah, so it'll be probably downstairs at the auditorium here, but it'll be, Wednesday the 14th.
Awesome. Some other groups, there's Sydney CocoaHeads and GDG Melbourne. So the Hack Night we run with GDG Melbourne, so if you're just into mobile development and that, it's good to make it to the Hack Night because it's not just Swift, it's Flutter, Android, and some other technologies. How to find us? Probably the best place is Slack, just because you can jump on there and speak to us. But we've got the Melbourne CocoaHeads website, melbournecocoaheads.com, and Twitter. There's also the Mastodon accounts, or Mastodon? What is it? Mastodon. Okay, we've got to add that, so to come. And there's some channels in Slack. So the meetup, if you're interested in volunteering and helping these nights run, jump in the volunteers group. If you're looking for work or Need people for work, jump in #jobs. And if you want to do a presentation, which I think everyone should, jump in #speakers. It's good to see what people are working on and, you know, different levels, and yeah, it's just cool to see people excited about Swift development. Let's open up with Amy, the month that was.
The month that was from sometime in the past until May. For those that don't know me, I'm Amy. Please use she, her as the pronouns. So, one of the things we love doing here is celebrating everything that the community has shipped over the past couple of months. One of them from our friend Zach, who runs the Sydney CocoaHeads, is Glucomate. So this looks at all of the Apple Health data around blood glucose levels. So if you're diabetic and you have a continuous glucose monitor and that data gets fed into Apple Health, this is an app that will do a really amazing job of presenting it and allowing you to understand what's going on. Another friend is Rudrank, who has presented remotely to the Melbourne crowd before. He has a open source framework called Musanova Kit, which looks at the private Apple Music APIs and just exposes them in a very nice way. Ben Thomas, who is around on the Slack a fair bit, shipped an update to one of his apps called Harken. Again, it's a music-themed one. Pretty good if you like that. Apparently some company called Alphabet did Google I/O this morning and is on now. Always good to hear what the Google people are up to. A lot of AI stuff, some new devices. It was all pretty cool. Always around this time of year, Apple does some Pride stuff. I happened to be over in Tokyo recently for Tokyo Rainbow Pride. Coincidence? Maybe, maybe not. Maybe not. But I got there and there were Apple people there, which was pretty awesome. And yes, Apple has done their usual watch band. Sadly, no Apple Watch Ultra band. And their dynamic, amazing wallpaper. Just don't go for the light one because it completely washes out all of your app icons and the text. And yeah, it doesn't look good. Probably one of the biggest things from Apple in the past couple of days is Final Cut Pro is now on the iPad next week. It's a subscription model because everything is. There's, a few limitations because of it being an iPad OS app, but it's actually pretty cool. A lot of really amazing creative people have thrown up videos onto YouTube, so go searching on that. Another amazing thing is Apple did a security patch for all of their devices with the current OS. So if you're keeping up to date, make sure you apply the security patch. They are always super, super important. Mixed reality rumours. We all know the rumours, we've all heard them. Something's going to happen at some time in the future. Not going to admit sources. I don't know sources. No one tells me anything. That's a good thing because I love to talk. And if I found out the details about this, I'll be like, yeah, here it is. It's amazing. So no one talks to me. I just hear what's going on. Swift evolution. So Swift this time of year gets a whole heap of new stuff. A lot of it's been discussed before. We're hoping to get Swift 5.9 with the next version of Xcode. Couple of really good things that we are seeing from Swift evolution, if you're using task groups, can now get this thing called discarding task groups. That's going to be 5.9. Swift SDKs for cross-compilation. Observability will be super, super big because it is, the TLDR on it is structured concurrency, but for the observable object published and state property wrappers. The never type is going to be conforming to codable, macros, lots of stuff around macros, and variadic types as well. So particularly when you're declaring something, you're not going to have to do type 1, type 2, type 3, all the way through to however many you're limited to. It's just this, ... and you can throw in as many as you want. And the really nice thing is there are 26 days until dub. Yay! Fun times. And that is all for the month that was. As always, if you want to present the month that was, get in touch. It is super fun and super easy if you want practice with speaking.
Next up, we have Simon Whitty with Neo with Structured Concurrency. This I'm super looking forward to, by the way. So, thank you for being here and good luck.
So we're seeing your
First one.
extending?
Yeah,
Cool.
beautiful. Cheers. Good evening, everyone. Great to be here. I'm Simon. I'm an iOS developer by day, but by night, or by the last year at night, I've been building a HTTP server with Swift concurrency called FlyingFox. And I kind of started building it because I think Swift concurrency has probably been the one feature that's captured my imagination the most over the last 10 years, probably since Swift itself has come out. I remember reading Chris Lattner's manifesto on Swift concurrency from 2016 or 2017, and then just tracking all of the changes until it was released. And like any good engineer, how do you learn something is you just build something that you're not very good at, and you refine it, you improve it, and eventually you start to learn and understand it. So this talk, it's not really getting into really technical details, but trying to bring together some musings of in my journey of building this. So we'll go through what FlyingFox actually is itself, from the Swift package that you can get on GitHub. We'll look at a little bit of its structured concurrency, how it uses it, some of the async sequences that it uses, and then we'll touch a little bit on some non-blocking I/O and things of how you can actually get some network, you can get some network communication using structured concurrency, and we'll look at FlyingFox, which is a submodule, and then to round it out, some tips when you're asynchronously testing things, because that can be a nightmare. So FlyingFox is a HTTP server. It's on Swift. It's written in Swift. You can run it on Swift 5.5 plus. It's lightweight. So the goal I really had was, you want this to compile, you want it to be zero dependency, compile really fast, be simple to use. And the use case, I have comes from being an iOS developer. So being able to integrate this with an app or to use it alongside an app to help support the test process is really the direction that I was coming from. So even though it's focusing on supporting apps, it supports Linux and Windows as well, just because that was more my curiosity on how you get all of that to work. I'm sure nobody actually runs it on Windows at all, but you can. Linux actually, it was really easy to get Linux to work, and I actually run it on a few servers in Docker, which is using Linux. It only supports HTTP 1.1 and WebSockets, which is good enough for my needs at the moment. So inside the package, you'll see there's the FlyingFox part, which is really the high-level HTTP protocol components that you kind of use. And there's another module that you can also use called FlyingSox, and that's really just a socket communication, and it creates the bridge for your to the async world. Because all the sockets that we use have been around for 30, 40 years, and it's just adding that bridge. I'm actually using it where I'm working at the moment to support the development process. I run a few low stakes HTTP or websites and services on it myself. I actually run it in Docker on Google Cloud Run behind their reverse proxy. So that's my recommendation of how to run it. But if you're really serious about Swift on the server, I would point you to Swift Neo. If you want high performance, you want it to be secure, standards compliant, extensible, if you want HTTP 2, look at Swift Neo. FlyingFox doesn't do any of that. They promise to do any of that, so yeah. But what Swift Neo will do, it'll take forever to compile. If you're on Intel, you'll be looking at least a minute, 2 minutes. If you pull in OpenSSL, it'll be even more. It's complex. You can do so much. So there's a bit of a learning curve as well. So if you're not wanting to pull all that in to your project, you might want something a bit simpler. It's also Swift System, which Apple put out. So this was a good reference for me. So this is really just a Swift wrapper on top of these low-level calls, which is multi-platform as well. But that doesn't support any async await calls, but that was a good reference for me. So the story for FlyingFox, it really starts, kind of here in the middle. This is the typical way HTTP servers work. You have a request coming in, and the server gives a response. And I was using servers to do some testing and support my process, and this was working exactly like that. And then I wanted to bring in async, because we all want to do that. And then I think everyone here is probably familiar. As you do that, these effects are viral. It spreads throughout the code base. The calling function needs it. And they're the really obvious effects. But it also spreads lower as well if you do things correctly. So we'll look at how it spreads upwards and how it spreads downwards in the code base as well. So this was really just all I wanted to do. And the next thing you know, I've built an entire server just to do this. So of course there's easier ways. You can take your function, you can wrap it in a task. So this is one way. You could do it this unstructured way. Straight away you can look at that and say, look, what happens with cancellation? What happens if you want to stop those requests? If you've just fired the task off and it's running, yes, it'll work, but you can't cancel it. So in FlyingFox, we use structured concurrency. So at the moment, we use a task group. You can see that we're waiting for connections to come in. Those connections are modelled via an async sequence, and then we start a new task for every connection to handle that, and that works really well. These are slightly wasteful. I think Amy mentioned SE 381. I can see it on my slide, which is discarding task groups. So that's coming in Swift 5.9. And the waste there is that every child task that you start with a server like this, you don't really care about the response. You just want it to end, and then you want everything to be discarded. So there's a few bytes that actually get leaked at the moment just with the throwing task group. Even though there's no result, there's a few bytes just in the pointer to the task and its structure itself. So Swift 5.9, I'm really looking forward to that. But as the concurrency spreads upwards through the code base, if you handle it properly with FlyingFox, you basically get this as your interface to start the server. So if your main.swift just imports FlyingFox, you can start the server just like this, and it will run, and it will run forever until it runs out of memory because we're not using a discarding task group. But yeah, and this makes use of top-level concurrency. So execution will be suspended inside server.start until an error is thrown. You can interrupt the process, but that's all you really need to do if you're using Docker to run FlyingFox as well. Is that there's a heap of support in FlyingFox for handling requests and doing things, which I'm not really going to touch on this evening, but you can kind of see that with a request you could return any response. And with those things in place, you end up with this nice structured task tree. So the server starts, and it starts 2 child tasks. There's a pool, which we'll talk about a little bit later. There's a listen task, and that's the task that's going to be listening really for your connections that are incoming. So that's constantly running. And when a connection comes in, that connection gets its own task, so it can handle the connection. And another connection comes in, it can handle 2 connections, and each connection then processes requests one at a time, but they just run inside their own task. When the connection finishes, it goes away, and finally the whole server goes away. So the top level inside FlyingFox kind of relies on a few async sequences. So the listening task that runs, waiting for connections, there's an async sequence that's that really just gives you a connection. So you can have that pattern where you do for, await, a connection, and every connection that comes in is sent in the sequence. So you can see there, it just pulls through there. The other sequence that we've built is basically like a byte sequence. And the sequence that I'm using is not buffered beyond what's buffered in the socket. So for a HTTP request, you basically need to process the header byte by byte, and once you get through the header, you can then process the body in larger chunks. And it's amazing that once you've got a single sequence of bytes like this, you can easily transform that into something a little bit more useful. So a sequence of bytes, you can use that to map that into a sequence of requests. And once you've got those components built, it almost starts to write itself. The code to actually run the server and parse the requests, you obviously have to write the HTTP protocol parts, but once you've got those key Swift concurrency parts, the actual management of the server takes kind of care of itself. The hard part is getting some of those pieces So an async sequence or a, I can't remember what else we mentioned. And the hard part is, because half of these, or all of these calls by default, they block. If you're not, and we want it to be non-blocking. If you're not sure what non-blocking is, it's probably easier to think about what actually is blocking. So I think everyone is probably familiar with this old API that's been around for a very long time that basically loads data from a URL. And if you load that from a network synchronously in your app, basically, you typically see the user interface lock up, nothing happens, and then it continues. And that's just because the API blocks while it executes it. So non-blocking API is API that doesn't block. So you're probably all familiar with just the completion handlers, which are non-blocking. They're so familiar to us, we use them all the time. And the newer APIs that suspend, so they don't use completion handlers, but they suspend, so they're non-blocking. So you actively want to avoid blocking, and especially in Swift concurrency. We see the user interface lock up, but and that looks bad, but blocking in Swift concurrency is almost just as bad for concurrency. So you can try naively to not block. You might think, I'll wrap this in a task like this. And yes, this might get something off the main thread, but it's still going to block. And it's going to block one of the threads in the cooperative thread pool. You can try even harder. And you think, oh, maybe I'll do a continuation. I'll basically do the same pattern, but it still blocks a thread in the cooperative thread pool. And the cooperative thread pool, Apple, it doesn't really have much documentation on it. There's some references. This is a good session in DubDub from a few years ago, Swift concurrency behind the scenes, that goes to explain some of the details. But I think they deliberately hold back some of the details and don't want to make promises in the language beyond what they've said here. But basically, the cooperative thread pool works by keeping the number of threads limited. So Apple, they promise that the number of threads used in your application in the default cooperative thread pool will match the number of cores that you have. So if you have a phone with 4 cores, there'll only be 4 threads processing your async events. And the benefit there is that there's a limited number of cores, or there's a limited number of threads running, but they're quickly switching processing coroutines, so the tasks getting processed want to be moving through them quite quickly. So there's less thread context switching and more coroutine switching. And because that means that actual threads are quite limited, they're quite valuable. So if you do make one of those blocking calls, you're actually blocking one of those really precious threads. And if you block them all, everything that you're running async in your app will actually grind to a complete halt. So the number one thing, I suppose, to remember is never block if you, in an async method or a task. And if you have to block, then try and do that on a dispatch queue. So the last resort, if you don't actually know that there's better APIs to use and you really want to use this data with contents of, at the last resort, then jump out to a dispatch queue. And that will at least block a dispatch queue, but will keep one of the threads, will keep all the threads in the cooperative thread pool available to process things. So with that in mind, FlyingFox is the module that provides that async interface. So there's really kind of 3 types in there. We've got this socket type, and that socket is it's my cross-platform overlay or wrapper that sits on top of the system calls that live underneath. So Linux and Mac OS system calls for sockets, very, very similar. They're basically functions that take unsafe mutable pointers. They take values. They return result codes. So my layer that sits on top of that manages all that specifically for each platform and Windows. And then any errors that it gets, it actually throws. So it gives you that nice affordance to, instead of checking error result codes and checking random global error number variables, it'll just throw. An async socket basically takes a socket and exposes it asynchronously. And to do that, it needs something to help with its blocking, and that's the async socket pool that I use. So when you look in the code, an async socket really just takes a socket and it takes the async socket pool, and that's basically your interface. The first thing you do, because by default sockets and file descriptors, they all block by default. So the first thing you do is set an option. So this is the high-level API that FlyingFox gives you, but this maps to a low-level system call. And you can set that socket to go into non-blocking mode. What that means is that now when you try to read data from it, it's not going to block like we saw before. It'll actually return straight away, and it returns with an error. So my overlay, when it's actually going to block, instead of blocking, it throws an error to say it's blocked, which is great. We don't actually block, but we don't know when data's going to be there. So we could loop and go, let's try again. Let's sleep for a few seconds. Maybe the data will show up, and that can all work. But it would be really nice to know when data is going to be ready. But that is actually quite a hard problem. So what FlyingFox does is it takes the pool and it uses the pool to suspend until something's ready. So the socket here, we try and read from the socket. There's no data there. It throws an error. We catch the blocked error, and we tell the pool, now suspend us until there is something to read. When there is something ready to read, the pool resumes the task. It reads from the socket again, and it continues. And it all kind of seems simple. And the problem is those APIs that you need to use to notify you that something's ready on a socket, they're all different on every platform. There is one high-level API, like the Windows version that's the poll version. There is a version that you can run on every platform, and that kind of runs in user space, and it's not as efficient, and it's not as it's actually a little bit more difficult to use. But Mac OS, there's KQ, and you basically can ask the kernel to tell you for a certain socket when is there any events available, and the same pattern is on ePoll on Linux. And it is just a little bit cumbersome because the semantics of those APIs aren't 100% aligned. So it's not just simply mapping names; it's also doing like some slightly different processing there as well. And then all these system calls all block as well. So while we've done our best to kick this blocking concept, or avoid blocking as much as possible, we've almost now got to the end of the line, and we've got these blocking calls we have to make just to be notified. So what FlyingFox does is it uses a dispatch queue to do that final call to block, that final blocking call to notify that there's data available for on the sockets. And instead of every connection having its own dispatch queue and basically having its own thread, it is using a shared queue. So every socket kind of shares the same pool, just to use that to share it that way. And if you might remember from earlier, we had the task diagram when the service starts. So that's the pool that runs at the very top. So every connection that comes in uses that pool to manage its own sockets. And if that pool throws an error, those tasks end, and then finally the server will end, so the start function will throw an error, and you'll see something printed in your console. And then testing this stuff. So building FlyingFox and building its tests and testing its functionality was very challenging. I think everyone's probably had experience with asynchronous testing. If you haven't used async away, you maybe have done some UI testing, and they're notoriously flaky and they're difficult to write. It doesn't matter how much experience you have, I think everyone can struggle and have problems with them, and it's just because there's so many combinations and possible states the system can be in, and it's really tricky to get across all of it. So there's some tips that I've kind of learnt that we can kind of go through. So adding logging I found like super important if you've got tests and it's not, it might be working fine when you manually just test it, but when you're trying to automate some testing and getting it to be reliable, it's failing sometimes. So adding logging is really, really helpful. So you can see that flow because there's so many layers in the system that's asynchronous. Working out exactly what the what was happening, so trying to observe all of those layers. So if there's logging in your system, it can help. And this was a big one. So avoiding overlapping tests. So by that, I mean you can run tests in parallel, but sometimes your test finishes and there's code still running. And when there's code still running, it could be doing something and the next test starts. So it can be handy to wait for the first test to almost completely stop. And if you want it to wait to completely stop, sometimes you've got to make sure that all the cleanup has happened. So if you've started the HTTP server and you cancel it, you might need to wait until the cancellation's finished and there is an error before you start the next one and you continue. And I had this really, really hairy bug where it was failing sometimes, some tests were failing sometimes on in some scenarios, and it ended up being like a bug in the app where this FlyingFox server was actually closing a socket twice. So you close a socket, and then when it was unwinding and all of those tasks are closing, it was closing the same socket again, and it was ignoring the error because the socket couldn't be closed. It didn't really exist. But if you know about sockets and file descriptors, they're really just numbers. And sometimes if you're super unlucky and the tests overlap, the next server has started and its file descriptor or its socket is the same number, and then the server that's shutting down is actually closing the socket for the next server. So it looks like this server just started, but it just died straight away. And yeah, just ensuring that the tests actually completely finish and tear down can help there. And test cancellation. So cancellation, a lot of the time I've found like a lot of people don't think about it too much, but if you're writing if you're writing continuations yourself, and if you're actually writing cancellation handlers, then I'd recommend testing it, because it's probably one of the toughest aspects, I think, the cancellation handler in Swift concurrency to actually use correctly. So I'd write tests that your tasks that you start, you can actually cancel. So in your tests, avoid blocking API as well. So even waiting for expectations like this, I think in recent versions of Xcode, it actually tells you now don't do this. But this was a real pitfall, very early on. And even other blocking API, you might think, oh, this is not in my app. I will. It's okay just to block here. It's fine. But even starving resources when you're running your tests can cause issues, because a lot of the time, flaky tests run differently on different hardware. And if you use these blocking APIs, it actually starves resources for your test itself, and it can make that more flaky. I think early on that I had written a test that was using expectations like this in an async method, and I think running it on a GitHub Actions node, which possibly only had 2 CPU cores, so that may have meant that there's only, or that would have meant there's only 2 threads in the cooperative thread pool, and just waiting for an expectation would mean my task was just never completing at all, and it was like really weird. You're like, why is that task just never completing? And then removing expectations, basically removing that blocking call fix the issue. Now, I think Apple now, they recommend use this API if you're using expectations. I actually found I don't actually need to use expectations in the asynchronous tests that I write. Repeatedly run tests. So if you didn't know, you can select a test in Xcode, then you can run it thousands and thousands of times. If you're lucky, your test will fail, like your test that's flaky will fail early, and it will fail repeatedly, so you'll be able to fix it. If you're really unlucky, you might have to run it up to 10,000 times, which I've found sometimes actually reproduce it. So the way you get this is, I think when you're looking at your tests in Xcode, it's normally like that little diamond that you can click and it turns green when everything's all good. So if you right click on there, you can say run this test repeatedly, and you can edit it and say run it 10,000 times. And the other aspect I've really observed is like different behaviour on different architectures, and that's I suppose that's expected when your tests are asynchronous, and they're there's issues. They're different depending on different circumstances of each machine. They're going to have different a different sequence of events and different aspect. So sometimes I've found that a test was only failing on Intel, and it's probably nothing to do with the architecture. Probably just because that machine runs it in a certain way. If you're running things on GitHub Actions, at the moment they're all Intel nodes. There's no Apple Silicon on GitHub Actions yet, and if you're using Apple Silicon, then it can be infuriating. So if you do have like another machine lying around, or if you've got access to some virtualization, you can try and run your tests in virtualization as well, and see if it's easier to make them break. Good. And that's pretty much the end. So thanks for listening about my journey through trying to build this FlyingFox server. And please take any questions if people have any questions or.
Yeah.
Thanks, Simon. Any questions?
Have you done performance testing with it?
Oh no, I should have mentioned in there that I deliberately haven't tried to performance test. So the performance tests I've done are basically serving Xcode on my machine through curl. So the testing I've done has like been a few connections. Or, what kind of throughput do I get through it? Not how many connections can I handle at once. And I tell myself that when I run it on Google Cloud Run, that its load balancer will just spin up more Docker containers for me when I need to.
I'm more interested about the XC-test performance features, right, where you can automate the testing of performance, but I guess you haven't done that.
Yeah, no.
I was going to ask something similar in terms of how you determined the dispatch queue was the best method to sort of stop blocking. Like, did you have any sort of test around what would happen or the implications of not using dispatch queue?
Yeah, so if you, so I've run some tests that if you just spawn a task, say a task group, and then you add in, 10, 20,000 tasks, that's fine. Swift concurrency will handle that. But if you put a blocking call in there and you see how slow everything will go through, you can either you can immediately grind it to a halt, and yeah, it's actually quite noticeable. So I think, yeah, and some of the tests that I have done, like you can start off and you can see there might only be a couple of threads running, and then if you try and spawn 10, 20,000 tasks, you know, within you know, a few seconds, there'll be, the tasks will all be running, matching the cores on the machine. And if you do the same test with dispatch queues, more and more dispatch queues and more threads, and you'll have thousands of threads. And that's one of the issues with dispatch queues, is the thread explosion that can occur. But if you're executing thousands of blocking tasks, then dispatch queues solution is to just spawn another thread so work will get done. So,
Any other questions?
Love the talk. Remind me a lot of uni days. So, a bit of a tangential question. Have you had to deal with any endianness differences, like big endian, little endian, or anything like that, or are you working at a bit higher of a level?
So when you run on Apple Silicon and ARM, the endianness is the same, and I think in the HTTP protocol everything's expected in the same endianness. I can't remember if it's big or little, but I use the one that the HTTP protocol standard uses.
Which is the correct answer.
Anyone else?
And yes, on uni days, I had, did socket programming like 23 years ago, and it was so much fun building this. Like, it took me right back to, when I learnt this, running it on the Yulara terminal with RMIT, all down this way, and yeah, it was great.
Good old BSD sockets.
Yes.
Thank you, Simon.
There you go.
Okay. Next up is Rob Amos, the man that needs no introduction.
No, not at all.
Unbreakable API Contracts with gRPC.
Pat, come back with that.
Okay.
Beautiful. So just the local presentation button. Can you read? Yes. Oh, no, I need a drink.
Okay. Just a quick drink break, and then we're good to go.
What an equivalent to one-man band.
Yeah, he's got
It's done.
Put to make the drum beat go.
Yeah.
All right, take it away, Rob.
Cool. All right. It's funny how things align. We didn't plan this, but tonight is apparently HTTP night. So I'm also talking about HTTP. We'll see how we go with whether there's any contradictions between the two. All right. So if you haven't caught one of my presentations before in the past, or if this is your first time here tonight, I can see a couple of blue dots in the audience. Thanks very much for coming along. My name's Rob. I normally go by Bok pretty much everywhere. That's my handle on Slack, on Mastodon, and that's what they call me at work too, so, I am one of the organisers here, but my day job is an iOS engineer over at ANZ. So as a bit of a background, if you haven't seen it yet, I actually gave a presentation on ANZ Plus, the app we've been building for the last 3 years. And I feel weird saying 3 years, it really doesn't feel like 3 years. I think it was May last year, so 12 months ago, up here on this stage. And at the end of this session, if you haven't seen that one, I recommend going back and watching that. It's on the CocoaHeads YouTube channel, and it's a really good insight to what we've built. So tonight, to continue the HTTP theme, I'm going to talk a little bit more about the underpinnings of the ANZ Plus app and how we build and manage the APIs themselves that drive it. So we're all familiar with this one, right? We should know what a HTTP request looks like for the most part. It has a bunch of headers that we send as part of a request, has a request body. It could be a JSON payload, it could be, heavens forbid, an XML payload, could be some other stuff, but it's a request and a response that has headers, that has a body. So let's add some structure to that, right? We're going to use this quite a bit, so we'll try to keep the colors good. Hopefully there's nobody red, green, colorblind in the audience. If so, I am sorry. Did not think that through. But the request we send is made up of HTTP headers and has a body, and the response is similarly made up of headers and a body. So I'm going to do some very poor attempts at being an enterprise architect here and put them into some sequence diagrams. So on the left-hand side, we've got the client. The right-hand side, you've got a server of some sort, and there's some messages going back and forth, right? I can see the only architect in the room shaking his head, so this is going well. The headers are obviously set before the message body as well. And then the response goes back the other way. Nice and easy. This is what we know as HTTP 1.1. So Simon covered that quite a bit already in his, with the request and the response types. And this was, yeah, HTTP 1.1. It's been around for 30, 40 years, probably 40 years, I think. But it's not best practice anymore. There's a new one, HTTP 2. And we're going to kind of evolve on this a little bit. It was more or less the same thing. HTTP 2 is just a request and a response going back, right? But for one, in HTTP 2 we generalize things a little bit more. And it's basically a series of what they call frames going from back and forth between the two participants. And the frames have different types. They simplify the terminology down a little bit because it doesn't really matter if it's going this way or if it's going this way. It's still a frame that has some headers and it's still a frame that has some data. So we'll just label it like that going through this. So we dive a little bit deeper into HTTP 2. They refer to each connection as a stream. The stream is actually one level above the connection, and I'll explain that. But a stream is a sequence of frames that goes back and forth between the two participants. So there can be multiple streams running in an HTTP 2 connection. That was one of the downsides of HTTP 1.1. It required a lot more actual connections between the two servers, whereas HTTP 2, so if you were to connect to google.com, in HTTP 1.1, they would do a new connection potentially for every asset you downloaded, so every style sheet, every image, every JavaScript file. But in HTTP 2, it will reuse the one HTTP connection and just open a different stream and multiplex the streams inside that connection. So because HTTP 2 is just a sequence of frames going back and forth between two participants, we're not actually limited to a single header frame and a single data frame. We can send as many data frames as we want, really, right? And you can take this as far or as long as you want. You can leave your HTTP stream open for up to as long as your network hardware will allow, and send as much data back and forth going in each direction. So whereas in HTTP 1 world, we had to build things like WebSockets that Simon was talking about to get around this limitations of HTTP 1.1, HTTP 2 has all of that built in. There's no need for separate things. And the way that it terminates, just to complete the loop, is you slap a end stream marker on one of the frames to let the remote end know that the stream is finished, pretty much. And that will cause the HTTP 2 implementations to close the stream, but not the connection. The connection stays open for the next stream that comes through, unless you choose to close it. So that's lovely for happy path flows, but what happens if something goes wrong on there? Well, it's not just multiple data frames. You can also send a headers frame at the end of the stream as well to provide on, well, some additional HTTP status, any metadata that you want to send, but it calls them trailers this time instead of headers. And one final note here before we move on. This is my only lecture on HTTP, I promise. One final note is that they don't have to go all in sequence. They can talk back and forth as much as you want. The only rule there is that there must be a headers at the beginning, and then you can pretty much do anything you like. All right. So now let's build on top of HTTP2, and we'll talk about gRPC. gRPC is the alternative to REST as a API paradigm that we are using for ANZ+. Now, it was originally a Google concept and a Google tool that they built out, but thank goodness it has graduated from Google. It means they can't abandonware it anymore like they did with Google Reader. I'm not hurt, I promise. And now it's supported by a number of open source, it's an open source project that's supported by a number of companies, including people like Apple. Apple has built stuff on top of gRPC. They support the Swift versions of this toolchain. But it builds on a very old enterprise concept of a remote procedure call, which is basically just a function running in a remote environment instead of on your local CPU. And in a way, Swift's distributed actors proposal is a evolution of this concept. Doesn't matter where your code's running, it's running somewhere, and you'll get a result back. So gRPC includes 4 different types of remote procedure calls. They have a unary request and response type, and then 3 different types of streaming that build on top of the HTTP2 capabilities we talked before. The first of these is a unary one, which is your basic REST style request and response. They call it unary because it involves a single data frame in either direction. And gRPC is intended to be protocol agnostic and language agnostic, so it differs slightly from HTTP2. There are other ways to use gRPC, including with JSON if you wanted to do that. But in gRPC terms, a data frame is known as a message, and the headers frame is known as a metadata. So I'll refer to that going forward. So for a unary call, the client will send the metadata headers and its message body, responds with its own metadata headers, a message body, and then the trailing metadata at the end. If we were to write this in Swift, it looks pretty much like what Simon had on his slides before, because it is basically a REST call, right? HTTP call. Method, async method, or throwing async method, takes a request type, returns a response type. The server streaming one, or second type that I listed on there, the client sends the metadata headers and your message body, same as your unary call, but the server then responds with one or more message bodies back, whatever it wants to do over time. And when it's finished, it sends the trailing metadata, and the stream marker to close the stream ends the call. In Swift, this would be the same as, instead of having the async method, it returns an async stream that will emit values over time. Basically how it works. No surprise then that the inverse of that is the client streaming one, which the client's the one that can send through all of the message bodies that it wants to, closes it off with the trailing metadata, and then the server will respond with its own headers, its own message response back, and then the trailers to close the connection. As with the Swift there, and I just realized that it's a bit cut off. Yay, go Pat. The Swift there is just the async sequence goes in the other direction, right? It's not too difficult, and then the server will respond asynchronously as it goes. So the final piece then is the bidirectional gRPC stream. As the name suggests, it's just a stream that goes both directions, and it can send as many message bodies as it wants, very much the same as a function that accepts async sequence and returns an async sequence. Cool. Cool. So here's a practical example of how that works. Back in May last year, when I did the offline data talk about how we do offline data at ANZ, I showed this slide. And it shows the app connecting to a remote command center instance in the cloud. And then it ingests commands into the local queue before running them and synchronizing data as instructed. So what I mentioned at the time but didn't really have much time to elaborate on is that this is just a gRPC server stream. Right, so we connect to the server, it just sends us back a bunch of stuff. So if we were to represent that on my terrible sequence diagrams, I'm sorry, Matt, it would look something like this. The ANZ app connects to the command center with a HTTP2 connection. It calls the get commands RPC. The message body that we send to command center is a marker, a stream marker, so it knows where to pick up and where it left off. And then it sends us back the headers, the initial metadata headers, any messages that it needs to send us, so any commands that are waiting to be processed, and includes in a marker with every one of those commands that we will save as we process things. And then eventually it closes off, right? So the marker that we save is obviously the one that we will use the next time we connect. So that way we can pick up exactly where we left off the previous time. And if something goes wrong, say we get disconnected or that sort of stuff, we know we can pick up exactly where we left off and nothing is left behind. So for one more example of that, which I didn't get into last time, we want to talk about how we get transactions onto the device. Like Command Center, the transaction stuff is a gRPC stream. Unlike Command Center, it's a bidirectional gRPC stream. So we make a HTTP connection to the transaction service, and we call the RPC to get the transactions. We send it a device ID so that it knows who we are. And in response, the transaction service will start sending us back any transactions that we don't know about. And each of those transactions will have a unique identifier that we can then use to acknowledge that we've received them. So because it's a bidirectional gRPC stream, we can send data in both directions. So we'll get a transaction, we acknowledge we've received that transaction, we've saved it to our cache. Everyone's happy, mostly happy. And this obviously goes on as long as it needs to go on. But if for any reason we're unable to send that acknowledgement back, so if we get disconnected, app crashes, doesn't happen, but if the app crashes, then the next time we connect, the transaction service would resend anything that we didn't acknowledge previously. So it works as a incremental sync of sorts. And then at some point we get disconnected. Right, so far I've spoken about the gRPC, which is the alternative to REST that we use, but I haven't really spoken about what goes inside those message bodies. It's not JSON. I put this slide in here purely so I can tap this button and use the next transition. I don't get to do this very often, but it's always very satisfying when I do. So here we go. Yay! So instead of JSON, gRPC is built on top of a format known as protocol buffers. Now, like JSON, it is intended to be language and platform neutral. Doesn't really matter what it's. JSON wasn't intended that way, it just kind of became that way in the end. It's also a serialized data structure like JSON, so we can send structures back and forth. But that's where the similarities end. It's a binary wire format, which means that it's sending binary data over the HTTP connections. It's not sending ASCII text or UTF-8 text if you do it properly. So it's not designed to be human readable. JSON's designed to be human readable. But the benefits of that is, when you take a JSON payload and you gzip it down, the same payload in protocol buffers will be 84% smaller than the gzip JSON. So it has a lot of efficiencies in terms of network traffic and that sort of stuff. And this is then the most annoying bit of protocol buffers, but it's also the best bit of protocol buffers if you use it right. It requires a schema to be shared upfront. It's not like a JSON payload where you can look at the payload and figure it out how you do it. You need to have the schema up front. If you don't have the schema up front, you can't encode messages in protocol buffers and you can't decode messages in protocol buffers. Well, you can, but you're going to end up in a lot more pain than not. Yeah. So one last thing, the Swift protobuf framework that we use for protocol buffers is written by Apple. It's built by Apple, it's maintained by Apple. It's an open source project, the same as Swift syntax or Swift format or any of the other Apple open source Swift initiatives. So this has got the backing of Apple, at least to that extent. Right. Did I miss a slide there? No, cool. So this is an example of a protobuf message type. So as a serialized format for sending messages back and forth, they prefix everything with message instead of struct, but it's pretty much the same thing. So if you would try and describe a bank account, for example, I know a bank talking about bank examples, that's easy, but it's good. It's familiar, I guess is the word I'm looking for there. So if you were to describe a bank account, it might have 3 properties, the BSB account number and account name. They're all strings, as you can see from that, and they're assigned to fields 1, 2, and 3 in the protobuf message payload. Not going to go too much more into the depths of protobuf. We had to talk about this earlier today at the office, and it goes into a lot more detail. We don't have time for that today. That would be another 40 minutes on top of this, and we have to give the office back, the space back at some point. But the field numbers in general are used for serializing and deserializing within the format, and they're very good for forwards and backwards compatibility, how it does that. But we can describe more than just the message types in protobuf. We can also describe the gRPC APIs themselves in there. So here's a basic bank accounts service that has a single RPC defined in it. It's a unary gRPC call, so that lists available bank accounts. You send it a message with the type of accounts you would like to filter for, and it will return a list of the matching accounts. Pretty straightforward. If you look at the declaration of that, it's actually pretty similar to the Swift code that we had up before. So it's very nice and easy for us. The repeated keyword in the list itself is basically how protobuf describes arrays as a shorthand. Now, so this describes a unary gRPC call, but what if we wanted to return a stream instead? It's literally a one-liner, same as we would switch from the return type from the type to an async sequence. You just type in the stream keyword, and it will take care of the rest for you. If you wanted to be a client streaming one, you put the stream keyword in front of the request type, and if you want to be bidirectional, 2 stream keywords. So it's pretty easy. But did you notice something similar while we're looking at the protobuf? It's just code. It's just a different language from what we do, but it's just code. And as developers, what do we do with code normally? If we're doing it right, we throw it in source control. And if you have an API definition in code lives in source control, you have an API contract. Whoa. So here is how we manage APIs at ANZ. Protobuf definitions for all our APIs live inside a Git repo. We're all very familiar with Git, or the other alternatives that my name is escaped me now. Hopefully nobody's using Subversion here still, right? We're all on Git. We have agreed standards for the types and language features that we'll use. So as an example, we have an agreed way of how we do dates, which is one of the biggest contentions with JSON. Is it going to come back as a ISO 8601 string? Is it going to come back as a Unix timestamp? Spec doesn't say. It can do what they want, and often people will do what they want. I've seen some very weird date formats and calendar representations over the years. That doesn't happen because we have a type that is specific for this sort of stuff. We also have agreed ways we do API lifecycles. So no more sudden breaking changes. We have a agreed way of how breaking changes are handled, how versioning is done, how deprecations are communicated and managed, all of that sort of stuff. And APIs are considered to be a shared resource. This is not some generated Swagger or handwritten documentation that gets thrown into a wiki or a Confluence site and then left there to rot because nobody bothered to update it or even knew it was there to update it, more often than not. It's a living, breathing bit of code that engineers and developers can read, reason about, talk about, and iterate on, most importantly. So, because it lives in source control, API changes then is just a PR. Anyone can raise a PR. Doesn't necessarily mean it's going to get approved, but you can raise a PR and start a discussion based on that. It doesn't just have to be the people that maintain the backends that raise the PR to start a new API version. Anybody can do that. And we're all used to leaving feedback and collaborating on PRs by now. We all do it. Backend engineers do it as well. So why wouldn't you do that with your API definitions? It's all very, very nice and easy, very familiar. And the final piece of the puzzle then is there are required checks on those PRs to make sure that the SDKs for those APIs can be built in all languages that are supported. So for that final piece then, in the home stretch here, let's talk about how we get those protobuf definitions into Xcode. And that's pretty easy. It's just done, like it's one code in one language, and you want code in another language, so we just transfer it from one language to another. Or more accurately, we use the Swift protobuf package provided by Apple and the gRPC folks to pass the protobuf files, and then they spit out some Swift code at the other end. And that has a whole lot of benefits that you don't really see until you actually start using this. Right? For the first part, it means you're not writing codable conformances anymore. Whether you use the synthesized codable conformances or whether you're using manually done codable conformances, there's no more copy-pasting JSON properties from your JSON payload into Xcode to make sure you don't accidentally typo a property name. There's no more codable conformances. It means you don't have to spend energy writing tests, unit tests, to make sure that your JSON coming from the server passes. It's not a thing you have to do. And then there's no more time keeping those unit tests up to date as your APIs evolve over the years. And it's not just Swift. Like, this is very much a Swift-focused talk, but it's not just Swift that's generated as well. You can generate Kotlin libraries from the protobuf. You can generate frameworks for Go, for Python, for Ruby, JavaScript, if that's your thing. Whatever you need, you can generate it from the protobuf. So that means as long as you and the people writing your backends are generating SDKs from the same protobuf definitions, that you're guaranteed that the protobuf messages that are encoded or created by the backend are passable by your front end. You don't have to write the tests anymore to confirm that. And most importantly, it means there's no more fragile JSON payloads. How often have your apps broken because the backend team accidentally started returning a double or a string instead of an integer? It can be quite common, especially if they're working in Node or something else that's not a type-safe language. Their IDE is not going to yell at them if they suddenly start returning the wrong type into what is effectively a dictionary with any as the thing, right? But the generated protobuf SDK, the types that are generated by protobuf, the code generation, are strongly typed. So you will start to get an error if you're sending the wrong thing through. So if they do that, it means that the backend code just doesn't compile anymore, and they have to fix the error before they can move on. So what does the generated code look like? More or less exactly like you would expect. It generates a struct that conforms to the message type. It has 3 properties inside there that all look like strings. The Swift protobuf message protocol is what handles all of the decoding. And there's a little bit of boilerplate that I've left off this slide because it would then get quite big and quite unreadable. But it's all just generated for you by the SDK. You don't have to think about any of that. The generated gRPC clients themselves are the same. It generates a protocol and a client implementation for you. And we should all be able to, that should all look pretty familiar to us. The bank account service has a single method, same method that exactly the same name that was in the protobuf code, that accepts a bank account's filler type, which would be a struct, and returns a unirecall handler that is specialized with the expected request and response types. You can see that it generates the bank accounts list response type as well, and the repeated list of accounts has been transformed into an array. It's all pretty clean. As for actually using that code, that's pretty straightforward too. You create a client connection, which is built on top of Swift NIO. So again, another common theme with Simon's talk from before. Everything seems to be built on top of Swift NIO these days, so yeah. So gRPC will call this a channel, again, because it's protocol agnostic as far as that goes. So once you've created that channel, you create your bank accounts client, which was the generated SDK code. You pass in the channel so it knows how to do the communications back and forth. And then you just use async await on the contents like you normally would. You can also wrap it up into a combined publisher if you're not at the async await adoption stage yet. Otherwise, there is also completion handlers that you can use as well. So, yeah, pretty straightforward. But the important thing here is that all of the communication, decoding, encoding, serialization, deserialization, what do you want to call that? That's all done by the generated SDK code, not code that you have to take responsibility for and test. It's just all generated. It's lovely. So, how do we generate those? And this is the last little bit. How do you generate them? How do you get them into Xcode? You use CI, like your GitHub, your Jenkins, sorry if you're using Jenkins, your build kites, any of the CI platforms that are readily available. It's just code that you're running at the end of the day. So this is the last part, and I promise it's worth it to see just how much of an impact this has on your code base. So we'll get there very quickly, I promise. But as a little bit of a side note, if you were here last month to see Marcelo's talk on using VS Code for Swift, this is actually what he's built with using VS Code. So there's no Xcode involved in any of this little bit. It's all Swift, which is lovely. So the process of raising an API request starts as you would imagine. You raise a PR, that PR is reviewed, CI checks run to make sure that everything can generate successfully, they haven't done anything illegal, and then it gets approved, and then it gets merged. From there, we tag a new version of the API, kick off a workflow to generate the Swift code using Apple's Swift protobuf framework, and the gRPC generation tools as well. We wrap that up into a binary XC framework. This is usually the heavy compilation step because it involves compiling Swift NIO, and nobody likes that. But CI does that, and not you on your Mac. And then we throw that up into a registry somewhere. But really, it boils down to this. You raise the PR, get it approved, the binary target's uploaded somewhere, or the XC framework's uploaded somewhere. You add a binary target to your package.swift file with the name, the URL, and the hash, the SHA for that package. And that's it. Xcode will download that, manage that for you, gives you just like any other Swift code that was compiled locally. It's very cool. In the future, when we get to Swift package registry support, this will be even easier. You won't need to look up the URL and the SHA anymore. It will just be, pass the package name and the version number into Xcode, and Xcode, Swift PM will do the rest. Swift PM is not quite there on this one yet, but we're getting there. And that's it, right? So just to recap, you want a new API version, you raise a PR, get your PR approved and merged, you bump your version number in Xcode. That's all that's involved. There shouldn't be any more than that. There's no going in and updating your codable definitions, no going in updating your codable unit tests. It's just done. If there are any changes to your generated code that Xcode doesn't like, it will throw a compiler warning. You go and fix those compiler warnings, and then you're guaranteed to have something that will be able to talk to the server without errors. Compiler guarantees that instead of unit tests, which is very nice. But if typos are the bane of JSON APIs, where in this process can humans make a mistake and typo something and make it go wrong? Well, there's really two places. If you make a typo in your protobuf definition, doesn't matter. It will be frustrating and annoying that all of your generated SDKs have a typo in them, but everything will compile, everything will serialize and deserialize, doesn't matter. And if you type the package ID or the version number wrong, Xcode will just say no. And that's why I went with the clickbaity title at the start that says Unbreakable APIs for this talk. It's pretty damn hard once that's all set up and working to get this wrong. But hey, Xcode will always find a way at the end of the day. And that's it. That's everything I've got. I'm happy to take questions now. I've written up a couple of answers to questions I expected because I didn't want to spend another 10 minutes talking about this. But yeah, if anybody has any questions, please feel free.
Anyone?
The big nasty one,
Yep.
versioning.
Versioning, yeah, which I didn't talk to here. So we include the version details in the package name. So it becomes a separate package basically for forward and backwards compatible changes. Like if you're adding a new field to an API, Protobuf will handle forwards and backwards compatibility for that for you, so you don't need to care about that so much. So we don't change the package name for those. But if you want to make a breaking change to an API or a behaviorally breaking change to an API, we require a new version number to be embedded in the package name, which means it gets a different URL path, which means you have to handle that on both sides.
Anyone else?
Over here.
I'm mostly a backend engineer, so
Yeah.
yes, maybe some stupid question. For the bidirectional stream, what's the use case for that?
So I had one example in there in the transaction stream where we're sending down data, we're acknowledging receipt of that data. But it could be, if you're doing a text chat app, you've got messages going back and forth is the easy example. Video streams would be similar, though you wouldn't use gRPC for a video stream, but it's anything that has two-way communications that can happen simultaneously.
But for bank
Yep.
app, right? So do you have what's the use case for do you have a lot of conversation back and forth at the same time?
So it's this one. Let me bring the slide up for it again. This one with the transaction stream, where we get sent a transaction and we acknowledge receipt of that transaction. So that's one message going this way to say, hey, here is transaction number 10. You bought a beer at the pub. And then the app itself will send back a reply to say, yep, we've got transaction number 10, all good. We've saved it, everything's good. So that's a two-way stream because you've got the message coming from the server and you're responding to that server, to that one inside the same connection.
So it's just probably the size is smaller, it's faster than the REST API.
Yeah, you could do that as, if you're in HTTP 1 world, you could do that as multiple HTTP calls going in each direction, but that's a lot of overhead. Every time you make a new HTTP connection, there's potential that it can fail. There's error handling you need to do for that. If you've got a connection that's open, it's stable, and you can just send data back and forth, there's no overhead, no connection, waiting for the connection to happen, all of that sort of stuff.
Okay. Is it required for to use with HTTP 2 or?
Whoops, shouldn't have touched that. Thanks, Pat. gRPC supports more than just protocol buffers. It does actually have a REST, a JSON compatibility mode, and it does support HTTP 1.1. It doesn't support all of the same functionality over HTTP 1.1 though.
That's it.
Thank you, Rob.
Thank you to our speakers, Amy, Simon, and Rob. As I say, Simon's one, I would have been happy just with that flying socks module, but definitely a lot to think about when I go home. Love the idea of other people doing the month that was. You sprung that on me, and I think that's a great idea. So if anyone's out there that wants to just do a quick summary of what happened this month, well, the previous month, let us know. And Rob, thank you. Thank you to our sponsors, Itty Bitty Apps and Blue. We couldn't do it without you. Don't forget about Hack Night on 17th of May next week. Drinks Night. Oh, shit. Drinks Night on May 30th, Tuesday at the end of the month. And beyond WWDC, Wednesday, 14th of June. We'll come out with more details when we know. And now, we'll go to the pub, Mitre Tavern. Thank you everyone for coming.